Hello. So today we want to talk about an extension to Gauss's method called Gauss-Jordan's method that has some advantages. So before we start that, I want to revisit what the geometry of solution sets are. When I do these sort of check-ins, these quick questions, one of the things I try to do is to connect what happened in the last class, or maybe the class before, to this class, to this discussion. So that's what's happening here. I want to look at three questions. The first is says this is a solution set of a linear system. I'm not going to give you the linear system because I want to talk about the sketch. I want to draw a picture of what that solution set looks like. And of course, the lesson that we learned last time is that this is a plane in this is a plane in R3. So I'm not a very good sketcher, I'm sorry, so that's why I use the word sketch or instead of draw precisely. So I'll do the best I can. So the idea is something like you have a plane somehow. See how I do. Did I leave enough room for the x-axis and the z-axis and all that kind of stuff? There's the z. Oh, I didn't leave it. I didn't do it right. There's the z-axis and the x-axis, and the y-axis is somehow, who the hell knows? So x, y, and z. Who the hell knows? Okay, so that's the solution set of some linear system, and the particular linear system isn't important. What matters is that we are somehow looking at a plane in R2. This is the set of all vectors x, y, z, which can be written in the form 1, 1, 2 plus, and then there's 2 where you have vector times a letter, vector times a letter. So it's 1, 2, 1, and I use the letter t, and then 0, 2, minus 1. My t and my plus look too much alike. 0, 2, minus 1 times s. Okay? Now, a person can make sense of those parts of the expression. We talked about this being the homogeneous part, and we talked about this being the particular part. A person can make sense of those parts of the expression, and we saw that last time. I'll use a pencil here. Pencil doesn't come out as well on this particular camera, but it gives me sort of a different color. So the 1, 1, 2, the 1, 1, 2 vector somehow looks like so. 1, 1, 2. Okay. It gives you, it's a vector that starts at 0, 0, 0, and whose endpoint is 1, 1, 2. So the endpoint of that vector just touches the plane. Of course, you can draw 1, 1, 2 anywhere in space, and it'll be the same vector, but I choose to draw it so that it starts at 0, 0, 0. And then what's the 1, 2, 1 and the 0, 2, minus 1? Why, if you draw 1, 2, 1, and I'm 1, 2, minus 1. If you draw 1, 2, minus 1, I didn't write the minus sign there, sorry about that. If you draw 1, 2, minus 1, then you get a vector that somehow lies in the plane. The entire body of that vector lies in the plane. I didn't start that 1 at 0, 0, 0. So the entire body of that vector lies in the plane. If the plane was colored red, that entire vector would be colored red, but only the very tip of that vector would be colored red. And of course, 0, 2, minus 1, same sort of stuff. 0, 2, minus 1. Also, the entire body of 0, 2, minus 1 lies in the plane. The entire vector would be colored red. Okay, so we can identify the parts here. The particular reaches out from the floor and just touches the plane. The homogeneous parts lie entirely within the plane. Okay. One thing I want to point out about this that leads into the discussion we're going to have moving forward, and that is that a person might think we're solving linear systems. A person very sensibly might think we're solving linear systems, and so I'm interested in the particular solution, the 1, 1, 2, because that solves the linear system. That's one of the vectors. When you plug it into the linear system, gives you the answers on the right-hand side. So this is what I'm really interested in. But that proves to be not really right. There's another point of view that proves to be the more fruitful one. And that is that what's interesting about this solution set is that there are infinitely many solutions. Where does that sort of infinite ability to make infinitely many solutions come from? And the answer is it comes from the homogeneous part. It comes from this vector and this vector. So the 1, 2, minus 1 and the 0, 2, minus 1 are sort of the interesting part of this picture. And the 1, 1, 2 simply takes you, it's like an elevator, it takes you from the floor, takes you from, excuse me, the entrance up to the floor you want to go. So in some ways I think of this, it's a little silly analogy, but it's the analogy that I like. So if you want to play tennis, if what you're interested in is playing tennis, then what you're interested in is what happens on the tennis court. And this vector here is taking you to the tennis court. This vector here is the actual court. So this is only taking you to the court. This is where the real action happens. This vector here takes you to the court, and these two vectors give you the real action, the infinitely many solutions. Now we see that when we go to the second question. If I bring back the second question, if I do it right, always a big if. Come on, there we go. It says find the particular solution vector for t equals minus 1 and s equals 1, and then sketch it. So find the particular solution vector for t equals minus 1 and s equals 1. So I'm simply going to plug in, this was 1, this is 2. I'm simply going to plug in t equals minus 1 and s equals 1. So I get 1, 1, 2 plus 1, 2 minus 1. Remember the minus 1 that time, times minus 1 plus 0, 2, minus 1 times 1. And I'm not very good with arithmetic, so I got to be super careful. So I'll do that as 1, 1, 2 plus minus 1, minus 2 plus 1 plus 0, 2, minus 1. And even I ought to be able to add those up. That's 0, 1, and 2. Okay, and it says sketch it, and the only point of the sketch it is to make you think of that vector as living somewhere in 3 space. So 0, 1, 2, 0, 1, 2 looks somehow like, I'll draw it like I drew the other ones in pencil. 0, 1, 2 looks somehow like so. Okay, and then part 3, for question part 3, and again it's always tricky when I bounce that one up, is I took the old set here, 1, 1, 2, and I replaced the particular solution with the 0, 1, 2. So I replaced the 1, 1, 2, what happens when you take t equals 0 and s equals 0, and I replace it with what happens when you take t equals minus 1 and s equals 1. And then it says sketch it. Right here, sketch this. And of course pop it down. Of course, so for part 3, the answer is C part 1. That is to say, it's the exact same sketch. It's the exact same set of solutions. If you change the old particular solution to a new particular solution, I could have taken anything value there and any value there. If you change the old particular solution to a new particular solution, it leaves you with the exact same solution set. Instead of having this way to get to the tennis court, in my maybe stupid analogy, you have a new way to get to the tennis court, like so. But it still takes you up to the tennis court, still takes you up to the plane. That is to say, in some sense, the plane is where the real action happens, and all the particular solution, you can swap out the particular solution for a new one, all the particular solution does is take you to that plane. So the solution set of this linear system, which I didn't bother to give you, is a plane in 3 space, and you start at the origin, you use a particular solution as the offset to take you to that plane, and the real action happens on the plane. So the geometry I'm directing your attention to is that this part here, the part we call the solution to the associated homogeneous system, this part here is what gives us the interesting behavior, the infinitely many solutions. And this part here, the particular solution, is not special in the sense that I can change it for a different particular solution and I get exactly the same plane for a solution set. Okay, so moving forward, we will be interested in the particular solution more than we are, we'll be interested, in the homogeneous solution more than we are interested in the particular solution. When we try to study what is it about solution sets of linear systems, what is it about these planes in 3 space or in general flats, what's happening there, we will be less interested in the offsetter than we will be interested in kind of where the action happens. Okay, let's bring that down and bring up what we want to talk about today. So far in this series of talks, we've been doing Gauss's method, and then spent a couple minutes trying to make some conceptual sense of what we got there, the solution sets of linear systems. So we did Gauss's method, and we're able to write the solution sets of linear systems in some organized way using the vector notation. And then we took a second to review, or maybe for some folks it might be a first look, but in general review what the vector description of the solution set has to tell us. Okay, and what I want to do today is I want to introduce an extension to Gauss's method, so-called Gauss-Jordan. I want to introduce an extension to Gauss's method that will have some advantages and that will tell us something about what we're doing. Okay, what happened? Why am I not? Oh, I see. There we go. Okay, so it's called Gauss-Jordan reduction. Apologize, hit the wrong button. It's called Gauss-Jordan reduction. So I have a linear system here, and it doesn't look especially doesn't look especially different than any other linear system we've been working with. I used Gauss's method to the minus 2 rho 1 plus rho 2 kind of stuff, and I got to echelon form down here, and we could absolutely solve the system. For example, it's plane from what I have written here that z equals 2. But I want to go on here. Instead of just doing back substitution, I'm going to continue doing row operations, and I'm going to go on to get the system, in some sense, completely reduced. Instead of having this junk up here, I'll turn those into zeros also. So we'll start off, I have a particular process in mind. I'll start off by, here I have a 1 in front of x and a minus 3 in front of y and a 1 in front of z. I want to turn all the coefficients of the leading variables into 1s. So of course I'm going to take minus 1/3 rho 2. And then I'll take that system, that right here is the same system as from the previous screen. I copied it because I didn't have enough room all on one screen. And I want to introduce a new kind of step. Before, I first use the x to eliminate, and then I use the y to eliminate both of them down. Here, I'm going to eliminate up. When you eliminate up, you don't start with x. Instead, when you eliminate x, you start and you work right to left. So I'm going to start with the z that's right here. And I'm going to use this row, row 3, to eliminate the minus 2/3 z, and I'm going to use this row, row 3, to eliminate the minus z. So we know how to do those steps, it's just that we've never thought to do them up before. So using the row 3 to simplify row 2 is to take 2/3 row 3 plus row 2. 2/3 row 3 plus row 2. We'll turn that into a 0. And you see it there, 0. I just have simply the y equals 3. Of course, when you take 2/3 of 2 and add to 5/3. So anyway, you get y equals 3. And likewise, if I want to use this row, row 3, to eliminate that minus z, then I need to take row 3, add it to row 1. Notice that the changed rows, as before, the changed row is always written second, and the row you're using to act on the changed row is written first. You've got to write them in some order. You might as well write them in the same order every time. So when you do this, you've used z to eliminate both of the things above it. So we're not only clearing out downstairs, we're clearing out upstairs also. And a person can guess what's going to happen next. I'm going to move from right to left. I'm going to use this y to get rid of that y with a minus row 2 add to row 1. So there we go. Now this method has a disadvantage that there's more arithmetic than with Gauss's method, but it has the advantage that when you finish, the answer's right there, just looking at you. So using one entry to clear out the entire rest of the column is called pivoting on that entry. So for example, I've cleared out the entire rest of the z column here, I've cleared out the entire rest of the y column, and I actually came to this screen with the x having cleared out the rest of the x column. It's called pivoting on that entry because of some geometry that we're not going to go into. So just, I don't like to do one example of anything, especially something very important. So I'm doing another example. You see here that this is a 3-equation, 4 unknown system, 3 equations, 4 letters. So I must be going to end up with a row, at least one row that does not have, at least one variable that does not lead a row. So just to do something different, I just thought to do a system that will have infinitely many solutions. Looks perfectly innocuous linear system, and it is perfectly innocuous. So of course we recognize the Gauss's method. It so happens that it takes only one row operation to do Gauss's method, and to get so that below this diagonal is all zeros. Only took one operation, and you get some other arithmetic, and it's not very interesting. Next step, so after you clear out below the diagonal, next step is to turn the diagonal into ones. So I have to turn the 2 into a 1, I have to turn the 5/2 into a 1, and that involves some other arithmetic on the row, but it isn't especially hard and it isn't especially interesting. The new part, the part that we haven't seen before, is to eliminate upwards, is to use the one that's here to eliminate above it, and to use the one that's here to eliminate above it. Now I couldn't fit it all on one screen, but to use the one that's here to eliminate above it, oh, forgive me, what did I do wrong? Oh, there it is. Forgive me, I lost sight of what I was doing. Use the one that's here to eliminate above it. There we go, takes minus 3/2 row 3 plus row 2. There we go. And then to use the one to eliminate above it takes row 2 plus row 1, and I end up with a system. Something was in my way. I'm sorry. So I end up with a system that it has this property that below the diagonal is all zeros and above the diagonal is all zeros, and there's some other junk simply because there are more unknowns than there are equations. So you can't have the case that every unknown leads an equation. So we have some other junk and some other junk. Here, the rest of the description, there's the matrix copied from the previous screen. The rest of the job is to put it into a description, a parameterized description of the solution set, and a person can't help but notice that just like on the previous problem where I said the disadvantage is more arithmetic, but the advantage is that it gives you the solution set plainly written out. Well, look, we've got the solution set plainly written out. It's just a question of transcribing it to write down the solution set. So this particular method here, you see that these have changed their sign, changed their SIGN. To write down the solution set is once you have this form, to write down the solution set is all very straightforward. So this Gauss-Jordan elimination has the disadvantage of more arithmetic, and when you're doing it by hand, then it can get a little uglier and you make a lot of mistakes. Believe me, I've made many, many mistakes on these over the years. Although in this computer age, I make fewer because I get the computer to do it for me. But it has the advantage that to get from this final matrix to the solution set is just trivial transcription. So this extension to Gauss's method is called Gauss-Jordan method or Gauss-Jordan reduction. Just a small historical word. This Jordan is not the same Jordan that will appear at the very end of the course. Just a coincidence that they both had the same last name. So just not that it matters, but this is called Gauss-Jordan method, and it's not the same Jordan as a Jordan you haven't heard about yet. Not the same as the Camille Jordan. So I'm going to call that form. I can't call it echelon form because I use that word for a different form. So I'm going to call that reduced echelon form. So a matrix or a linear system's in reduced echelon form if addition to being in echelon form. Not only do you have zeros below the diagonal, but you also have every entry on the diagonal is a 1, and every leading entry is a 1. And it's the only non-zero entry in its column. So you've pivoted on that entry and cleared completely out of that column. And again, the cost of Gauss-Jordan reduction is that it takes additional arithmetic. People have spent a lot of time in the computer age counting the number of steps that each method of solving a system takes, and it turns out that Gauss's method takes fewer steps. So the cost of Gauss-Jordan reduction is the additional arithmetic, but the benefit is that the solution set is quite plain. It will have other benefits for us also, but in particular at this moment, it's perfectly clear that that's a benefit. Now I want to talk about some of these other benefits. The first is that what we're going to occupy ourselves with today is that I want to point out that that we get something about the solutions, about the solution matrices. First, an observation. Elementary row operations are reversible. When I do Gauss method here, or Gauss-Jordan method, there we go. When I do Gauss's method or Gauss-Jordan method, I have a mental image that I start with some kind of mess and I end with something that's very neat. So that is to say, I have a mental image that I proceed. This one comes after, and then comes after, and then comes after, and then finally I arrive at my goal. So I have a sense of some kind of that they proceed in some order. But in fact, that proves to not really be perfectly right. If I do Gauss's method on a matrix, any of the Gauss's method operations, if I do any of the Gauss's method operations, the elementary row operations, on a matrix, then I can reverse them. So for example, if I write down a matrix A and swap row I and row J, and then swap row J and row I, I'll be back to the original matrix again. If I write down a matrix and multiply row I by k, if k is not 0, and then multiply row I, same row, by 1 over k, I'm back to the original matrix. If I write down a matrix and take k row I plus row j, and then do minus k row I plus row j, I'm back to the original matrix. You notice in particular that the third case requires that i's be unequal to j. This also has a restriction that k can't be 0. And we somewhat artificially put in the restriction that I and j are not allowed to be equal for row swaps. But all that is a minor point. The major point is that each of these row operations are reducible. So whereas before I thought of myself as naturally going from upper left to lower right. In fact, I could, if I wanted to, if for some perverse reason I wanted, for example, if I wanted to make a homework question, I could go from lower right and make my way back to upper left. So that is to say, it's a little bit of a linguistic problem that I describe myself as reducing from here to here, because in fact these are interreducible. It's not the case that this is somehow lesser or after this. In fact, they are sort of equal to each other. I can go from the one to the other, sensibly go from the one to the other. So we say that matrices reduced to each other are equivalent with respect to row operations. It's a little awkward phrase, but the point of the phrase is to give some implication that you should not necessarily, I'm asking you to not necessarily think of the reduced matrices as somehow later or lesser. That in fact they're the same. They contain exactly the same information as the original matrix. So the way that you write this down formally is you describe the phrase that the matrices between matrices reduces to via elementary row operations is an equivalence relation. Been my experience that sometimes people taking this course, many times people taking this course, have not talked about equivalence relations or have not talked about it very much. Sometimes people have taken this course having already had the proofs course, and so they've taken a proofs course that described equivalence relations. That's great, good for you. But for those folks who have not, I'm going to play down a little bit the technical phrase equivalence relation and play up a little bit more the intuition. And the intuition is exactly that. Although we think of this matrix here as being somehow after this matrix, that's not really sensible. We can in fact go from this matrix over to this matrix, and I do that sometimes when I'm making homework problems. That in fact all of these matrices 1, 2, 3, 4, 5 are interreducible. They're all collected together in some sense. They're all somehow the same. They contain the same information as each other. So they are equivalent in some sense. The technical jargon is equivalence relation. They're equivalent in some sense. They are equivalent in the sense that they all somehow contain same linear information. We'll describe them all as row equivalent. The picture to have here is that I've broken the collection of all matrices, the previous slide, so 2 row, 3 column matrices, but in here I could have all matrices. I've broken the collection of all matrices up into different equivalence classes. Inside of a particular class are matrices that are equivalent to each other. So on the prior slide, I had 5 matrices, 1, 2, 3, 4, 5. All of them go in the same class. They all can be interrelated to each the other. Isn't that a terrible phrase? They're all interrelated. So I could stick all 5 of those matrices in this section here, and they're all row equivalent. So one thing that we're seeing is that Gauss's method, Gauss-Jordan method in particular, enables you to break the universe of matrices up into different types of matrices. And one type of matrix is this type right here, is the matrix that contains whatever this kind of information is. Okay? So we break the universe up into row equivalent classes. Okay, very good. Okay, so let's see here. Next time we're going to talk about, oops, I went too far. Next time we're going to talk about the linear combination lemma. So I'll put that slide up, and we'll see you then next time. Very good.